Hello everyone, I'm Kshitij and I'll be talking about the candidate optimization techniques that we are using in the Spotlight real-time system. So Ujjwal just talked about the real-time pipeline. I'll be just going more into the detail and mention what are the different techniques and methods we are using to reduce the huge number of candidates that we get and why we are trying to basically limit the number of candidates. I'll be also mentioning that. So again, this is the entire pipeline which has been shown again, and I'll be concentrating on the transient search pipeline here. So why we need candidate optimization? Whenever we are doing any single pulse search, usually you get thousands to millions of candidates in the time that we are searching for this single pulses, and we cannot possibly store or record or even just analyze all those millions of single pulses. So the idea is to reduce those number of candidates as they proceed in the pipeline so that we have a fewer number of candidates which we can look into. So, and the constraint, the main constraint why we have to limit the number of candidates is the storage constraints. So Spotlight currently has about 2 petabytes of storage, out of which 1 petabyte will be used for long-term archive, whatever the final good detections that we have and many interesting sources that we have found, those will be stored in those 1 petabyte storage, all the data regarding that. And 1 petabyte storage will be used in the real-time pipeline for the data dumps, which are the visibility dump and the raw voltage dumps. And those, you can see the rates here, they are quite high, 12.5 GBs per second for visibility and also 12.5 GBs per second for the raw baseband data. So together 25 GBs per second, that is the rate of the data that we are having. And we will be, for every trigger, we will be storing about 30 seconds of the data. So out of 1 petabyte storage, let's say the 50% of it, which is a 500 TB, will be getting filled in 1 week. If we want to retain those data for 7 days, just to have a look at it later, just to have, confirm that we have proper detections, what are the features that we get out of it. And if it's nothing is there, just remove that data. So that is for ourselves, we have put this condition that the data will be retained for 1 week. So that will take 50% of the storage available. So if and this is all considering the triggers are at 1 trigger per 10-minute rate. If you go higher than that, the data storage will be filling up quite quickly. So that is one of the constraints. And other constraint on the real-time pipeline is that, as Ujjwal mentioned, we are having something called as FRB SHM, which is about 400 seconds. And the real-time pipeline processes about 100 seconds of block each time. So the processing and the triggering, that is as soon as there is a event detected or a good candidate detected, we will be triggering the recording of the visibilities and raw voltages. That should happen within those 100 seconds because the next 100 seconds, the next buffer will be coming up. We have to finish the processing within that. So basically, that's what real time means. So that is what constraint that all the processing that should happen within 100 seconds. So this is the overall pipeline, the real time pipeline that we are having. The single pulse search, the Ujjwal talked about. The candidate optimizer part, these are the different sections in this pipeline which we'll be using to reduce this number of triggers. So the first thing what we will be using is the clustering. So for basically clustering is whenever we are doing single pulse searches, the single pulse search happens across different DMs. We are trying different DM trials, and many of these single pulse candidates will be across similar DM because we are trying so many 2,000 DM candidates with very small steps. So whatever the candidate you detect will be detected across multiple DMs and across different and very close times to each other. So basically what we want to do is we want to cluster them together and just pick up the best candidate present in that cluster. So to do this clustering, we use something called as DB scan, which is like a density based spatial clustering. So here you can see one of the example of this where there are these different clusters that are present in the data. The DB scan goes and finds this cluster. The parameters that we have to give is epsilon, that is what is the neighborhood radius that we want to be considered as for one candidate to be its neighbor, and another is the minimum number of samples that we want in the cluster. So this, based on this, you can see how this clustering has been happening here. And advantage of DB scan is it doesn't require any predefined cluster count, so it can itself go and check out what are the different clusters present in the data. So for our purpose, we are using DB scan, and here you can see one of the observations how the DB scan looks. So this is the DM and time plane, and here we are finding different clusters. DB scan just whichever the individual isolated points are there as considered as noise, which are basically RFI, so they are removed. And out of each cluster, then we select the best candidate, which is having the highest SNR. So now this entire thing is implemented on a multi-node. So as Harsha mentioned, we are having different sets of, in our cluster, we are having different sets of servers, basically different nodes. And for real-time pipeline, we are using 16 nodes. So on each node, we will be having different beams. Whatever the beams that are formed through the correlator will come through the next stage. They will be divided among these different nodes. They will go on this different node where the processing will happen. Clustering will happen on a single beam, individual beams. And this we have implemented using QML. And here you can see we are doing it on DM time arrival, DM and time of arrival plane, which after clustering the number of candidates from about thousands to millions are usually reduced to thousands of candidates per beam. Now, next step is, before going into next step, I'll just like to mention what other processes that we are working on, because this work is very active now. We are presently trying very hard to get best out of the candidate optimization. So this is the reason I'm telling this, because I would really like to have conversation with people who are experts in this and give us suggestions what we can implement and what we can improve. So please feel free. I'm just telling you what are the different methods that we are trying. But if you have any better suggestion, please come and tell us. So after DB scan, we are also trying to consider HDB scan, which is the hierarchical DB scan, where the DB scan is very much dependent on the epsilon values that you give and the clusters are formed. So we have noticed that the clusters are sometimes usually very larger. It goes for a very big kind of clusters, and sometimes that results into missing a real candidate, and sometimes that results into getting a RFI as a true candidate also. So we want to get rid of that. So presently we are trying this hierarchical DB scan, where it basically forms different structure based on different epsilon values, and then optimally selects which is the best kind of structure available, and then gives the different clusters available data. So here you can see one example where this is the DB scan and this is the hierarchical DB scan. And here you can see basically, especially at low DMs, it founds everything as a single cluster. But where in HDB scan, you can see it has been divided into different clusters. So we are not losing any important candidates, which retains the purity and completeness of the data. So this is what something presently are working on, and hopefully we'll be implementing it soon. So now once the clustering, that the beam level clustering has done, we move to something as sub-beam clustering, sub-beam filtering. So what we do is, as I mentioned, on each node we are having different sets of beams. So we combine the candidates out of each beam, because now any candidate can arrive in multiple beams at same time and same DM value. So now we want to just get rid of those redundancies. So the first step here is we apply a DM and SNR threshold. Why we didn't do this in the previous stage is because sometimes for clustering, a low DM and low SNR candidates are also important to get those cluster. So in this stage, we just get rid of the low DM and low SNR candidates, which are just spurious candidates. Then we combine across different beams, we combine the candidates having similar DM and similar time of arrival, and then just select the best candidate out of that. And the one RFI rejection technique that we are doing here is a kind of anti-coincidence filtering, where the beams that are given to a particular node to process are not sequential beams. We give beams to each node which are quite random and separated in space. So each node is basically processing beams which are far away from each other. And if there is a true genuine astrophysical source, it should be in a close by beams only. It should not be all over the place. But whereas RFI will be at all over the place with a strong signal to noise ratio. So this kind of in this technique, what we do is we just look if the signal is present on that node, whatever the beams are present. Is the candidate present in most of these beams with high SNR, then it should be a RFI. So we flag it and reject it. And that helps us in reducing a lot of RFI candidates. So at this stage, on that node, in that buffer, we get about 100 to thousands of candidates. So we have gone from 1 million of candidates to about 1,000 of candidates by just applying these two methods. And the next stage is the classification. So classification again, because there cannot be a human just checking all the possible candidates and confirming it's a true candidate or not, because the system is working in real time. So we need an automated classifier which will just take the features that has been extracted from the candidates and tell us it's a genuine candidate or an RFI. So for this, we are using Fetch, which is a it's a deep learning model, deep learning binary classifier, which will classify it as an FRB or an RFI. So this is implemented on hybrid CNN structure. It uses it uses two different kinds of model called DenseNet and exception. These models combined together help in both finding the richer, finer structures in the burst and as well as the broader DM signatures that we get in the data. It will look into this both, and the two features that we give to this this model is, you can see here are different layers. So the features that pass through these layers are dynamic spectrum, which is the frequency versus time, the de-dispersed dynamic spectrum that we give, and another is the DM time transform, which is at different DM tiles. What is the time series that we get? This kind of signal, it passes through these two layers, two different models, and then gives us the final output. If it is FRB like, it gives a label 1, and if it's a RFI like, it gets a label 0. And this work has been, fetch has been implemented on a framework called TensorFlow. And with this, you can see that how we classify the candidates. So here you can see the correctly classified label 1 candidate, which is a pulse from giant pulses from a pulsar, and this is label 0, which is just some spurious candidate coming. So the fetch correctly classifies these candidates, and after this classification we get about 10 to 100 candidates per node. Still there is a lot of modification need to be required in classification. That's why again we are presently trying to improve the classification. The existing TensorFlow version of Fetch is quite slower, and also it's very dependency heavy. It takes long time to load the model and process the data. So that's why we are trying to migrate it to ONNX framework. Now ONNX is an open standard format to representing the ML machine learning models. So which will, and also it helps us to use other runtimes such as TensorRT, which is quite optimized for NVIDIA GPUs. So we will be using TensorRT acceleration. We are using A100 GPUs in our cluster. So for this, the TensorRT is quite optimized. So we are trying to migrate to this, and we are trying to use something else, quantized version of Fetch, where usually in the Fetch you get something like you have to process float 32 data, and which is quite slow. So we are trying to see if we can even 16-bit or 8-bit numbers calculations can be done. So the classification will be much more faster. So this, by applying these changes, the changes have already been applied in some level, and I'm already seeing the improvement. So we are seeing about 5 times faster interface change. The GPU requirement for the memory is also lower, and we get improved accuracy also. And also we are planning to train the model with much more higher number of candidates also by getting some data from other observatories, from GMRT and some artificial data, just to train the model better. And now after the classification, till this stage, everything was happening on different nodes, each node having multiple beams. Now finally, we want to combine the candidates from all over the nodes, that is all the beams together. Here at present, the basic thing that we are doing is, if the candidate is present in different beams at the same DM and same time, just select the best candidate, the highest SNR candidate, and that will be our trigger. But something that we are presently working on is trying to see the signatures of the PSF itself in the data. So that means we will trying to do something called as match filtering with the beam available. So here is an example of a RFI which is present in all the beams, and here is a example of a true candidate which is present in the beam. So now you can see if it's a true astrophysical source, it will be concentrated near the beam center or wherever we are interested. The source is present in the data, but it will be present only quite lesser number of beams compared to RFI, which will be just scattered everywhere. So we are trying to use this itself to finally say, is a true candidate or is not a true candidate. So what we will be doing is, we will be taking the SNR map that you just saw. This is the SNR map that we get. We will be first making it, like smoothing it with a Gaussian filter. And then we will be convolving it with the simulated PSF. Every observation we will be getting based on the time and the location of that location in the sky that you're observing. We will get the simulated PSF, and we'll try to convolve it, which will result into these two kind of different outputs. If it's a RFI, this convolved output will be very much scattered everywhere. If it's a true source, it will be concentrating on a real on a smaller scale. So we are trying to find some statistical method that we can distinguish between this. Also, the plan is to use again a classifier here itself. So that classifier will tell this was true candidate or not. So there are 2 levels of classifications that will be happening. And then so this is again also is ongoing work. So anyone has any suggestions and ideas of how to filter these candidates, again, please come to us and let us know. So now I'm just showing how the pipeline is working. So we are at different stages of the real-time pipeline. We can see how the candidates are getting removed, and we are getting fewer number of candidates. And this is a true pulsar candidate. So you can see most of this, we try to get rid of these different redundancies. And at the end of this, only one candidate will be coming out. Whereas if it is RFI, you will see most of at different stages, we just get rid of this, most of the RFI candidates, but still somehow one remains, that is the classifier is not able to classify it, and that's why we are trying to improve the classifier. That's how the system is working as of now. We started commensal operation since few months, and during the commensal operation we tested the real-time pipeline, and the trigger that we are getting is about, the average trigger that we get is about 4 triggers per 10 minutes. But if you remember, our trigger rate was about 1 trigger per 10 minutes, that will be sustaining the constraints, the storage constraints, and as well as the real-time imaging constraints, because we want to dump the triggers successfully, like give the trigger successfully and dump the data which will be used for processing later, and also we'll be doing real-time imaging. So we also don't want to lose that. We don't want to lose the real-time localization. So in that case, 1 trigger per 10 minutes is the required rate. So we are having about 4 per 10 minutes. So we are quite not there yet. Well, we are trying our best to get that result. So the status of the pipeline is the 160 beam commensal system started from April to 2025, which is offline processing. The data was dumped and it was processed offline. Whereas from just September, just few weeks back, we started the real-time operation. It's under testing now. As I mentioned, the results we are getting are quite optimistic, but still a lot of improvements are required. We are testing the pipeline with 320 beams. And from the next JMRT cycle, which will be starting in a couple of weeks now, the fully real-time operation in cycle 49 is expected. And this is one of the crab gen pulses that we detected in commensal operation, and hopefully in next cycle we'll be detecting some FRB also. So yeah. So to summarize, the ongoing developments are there. Any suggestions, any ideas are welcome. Thank you. So yeah, this is the entire team. Many of the people are present here. Thank you.
Thanks, Kshitij. Questions? Once.
Okay. So I was just wondering about your classifier, which was trying to look for a localized signal for astrophysical sources. Yeah. I was wondering how it does with sources that are detected in the edge of the field of view.
Yeah, presently we have not developed a classifier which will do this. We are trying to work. Okay. It's an ongoing work. This is the idea. Presently we are just thinking if we can do any statistical method like the peak versus the deviation that we get around, some kind of statistical method. Mm-hmm. But to have a classifier that we need to train the model, and from based on a couple of discussions last week, we know the model is as good as the training data that you use. So we have to have a good training data also. So we are thinking how to go about this. This is not implemented yet. Okay. This is ongoing work.
Sounds good.
But hopefully, if the model is trained well, even if the object is present in the side of the field of view, still we should be getting detected. Hopefully.
Okay, I mean this may be like a very stupid question, but then, so if I understand right, there is one place where you do per beam, and then the beams all get mixed.
Yes.
Which you do like kind of anti-coincidence.
Yes.
That you mentioned about. So is there any fancy technique where you are waiting for beams to all the beams in the same node to sync or something? Or
yes. So what I mentioned is the global filtering part here is there. When all the beams will become close, all the beam candidates will be got into same node, and then we're processing everything together. This is the final stage.
For this, you talked about another.
Yeah, this is sub-level. This is just the beams that are present in that particular node, which are scattered around. So we will be filtering around first the node level filtering, and then it is the global level filtering at the end.
Beams
Yes.
from all over the place.
Yes, yes. So now, for example, if we are having 160 beams, we are having 16 nodes. So every node will have 10, 10, 10 beams, but which are not sequential beams or not close by beams, but all the scattered beams in that particular node.
Out of curiosity, did you ever try using the classifier before doing this sub beam level?
Because the number of candidates will be huge. Because at this stage, if you go before this stage, the number of candidates are about 1,000, and again classifying those thousands of candidates for individual beams. And that will be, so it will be multiplied by the 16 into 160 beams, that kind of number. So it will be too much too. So that's why you want to reduce number of candidates first and then use the classification. Yes, yeah, sure.
Yes, thanks. Great work again. And it's great to see that you're trying to speed up fetch, because I see a similar thing that it takes, 90% of the time to load the modules before it actually does anything.
Yes,
so
yes,
that's
exactly,
great. I'm
yes.
really looking forward to that. Related to that, and maybe it's actually more a question for the previous speaker. I also see that CandMaker, so yours CandMaker, takes forever to actually make candidates, right? So if you have 100 candidates, a lot of time is spent on just making those H5 files.
Yes.
With Candies, how does that perform? Is that any faster?
It is faster compared to the your CandMaker. So it does faster, and also the thing is it zooms into the dynamic spectrum. So your CandMaker goes for a very wide range of dispersion measure. So it goes from 0 to like 2000 or something and just makes it. But the update, the Candies, which is just based on your, but what it does is zooms into the dynamic spectrum. So it doesn't go for the entire DM range, but just the DM range, two ranges like above and below. So if you can see here, whatever the DM that we are expecting, it will from 60, 56, so it will go from 0 to 100. That's it.
Sure, no,
It doesn't go till all the DM.
we got that.
No, so we are not zooming into the DM, the dynamic spectrum. We are zooming into the DM transform. So what that does is, ideally your CandMaker will do it from 0 to twice the DM of the candidate. But we don't do that. So we select a much smaller range of DMs. So that because of that, it will be much faster, because we know that the slowest part of your CandMaker or Candies or whatever will be the DM transform. That's the slowest part of making the feature. So that will get reduced. So that's one thing. Plus, we are trying to optimize it better on the GPU itself, because your CandMaker just does it very simply using number. We are trying to just optimize our kernel so that it just works better. I think our current kernel is quite fast, but we are trying to see if we can go to say bfloat 16 to get additional speed ups, or maybe modify the kernel further. Yeah. That's part of the,
If I may, just one very last quick question.
Yeah.
Did you ever try or test in your pipeline where your sort of bottleneck is, where you spend most time in your, you had some, I don't know, of order 10 steps. Do you know where you spend most time?
Candidate making itself is taking, as you mentioned, this itself, though is faster compared to your, but still it's much more time consuming and slower. So we are trying to again improve this. Yes.
And one small thing, you talked about fetch being slow as well. Currently, what I have seen is, the Onyx version of fetch is there. That is much better than the TensorFlow version. So it is quicker. Even on the CPU, it's much quicker than the TensorFlow version. So I would advise you to give that a try. I think that will work better. Yeah.
Okay, so Prabhu, okay, one last question, because we are eating up the break.
Sorry, this is probably a question to many of you. How long you can continuously run Spotlight backends without worrying about can it run 24/7?
Yeah. So we have we have tested it. We have tested it for
not that
10
way.
hours,
The
11
pipeline
hours.
Logs or any cleaning up of the buffers or so.
Yeah. So the buffers and everything. So for example, if you are having multiple observations, still at every cycle, all the cache and everything gets cleared, and we move on to the next when the scan stops. Not the scan, but the observation. So that happens. And also we are, whatever the data comes is in shared memory format. So we are, as the data is just buffering through this. So we can just wait, like we can just run it for as long as it runs. So we have run it for maybe 11 hours, 12 hours, and it has not shown anything. So it can run for even 24 hours, 24/7. Yeah.
Okay, let's thank Kshitij and all the speakers of this session.